In geometry, continuous deformation means we can stretch and twist a shape into a new form without tearing or breaking the space it occupies. In 1, 2, and 3 dimensions, continuous geometry and smooth calculus are perfectly aligned. If you can continuously deform one shape into another, their underlying smooth structures naturally match. Move up to 5 dimensions and beyond, and a mathematical framework called surgery theory completely resolves these classifications. We have established definitive maps for these higher spaces. But in exactly 4 dimensions, and only 4 dimensions, this alignment shatters. A shape can be continuously equivalent to another, but completely reject the same smooth coordinate calculus. Because 4-dimensional space is the sole environment where continuous geometry and smooth calculus divorce, it remains the most unclassified dimension in mathematics. To map this anomaly, we have to separate these two properties. Topological equivalence, or homeomorphism, is strictly the ability to continuously deform one object into another without tearing the space. Smooth equivalence requires a mathematical coordinate grid to transition between shapes without kinking, but the transition fails when a localized kink destroys the calculus. The continuous shape remains intact, but the smooth mapping equations crash at the fault line. This gives rise to an exotic manifold, a 4-dimensional space that is topologically identical to a standard space, but smoothly incompatible with it. The following chapters explore why standard analytical tools fail to classify these 4-dimensional spaces, and how topologists are forced to physically engineer them from scratch. Understanding exotic 4-manifolds is a process of uncovering the hidden structural limitations of calculus itself. In 1982, Michael Friedman mapped continuous 4-manifolds using algebraic matrices called intersection forms. These matrices provide a clean, definitive mapping of continuous topological spaces. By reading the intersection form, you can capture the continuous shape. But to differentiate the smooth structures, mathematicians rely on gauge theory. Developed through the work of physicists and mathematicians like Seiberg and Witten, this method requires solving nonlinear partial differential equations on the manifold. Gauge theory equations attempt to map the specific smooth structures that the algebraic intersection forms miss. There is a strict mathematical bottleneck to this approach. Gauge theory requires the manifold to have a high second Betti number to function. This integer measures a specific type of topological complexity. If we try to study a simple space, like the 4-sphere, where the second Betti number drops to 0, the invariant is undefined. The partial differential equations simply dissolve and fail to map onto the grid. This creates a deadlock. The algebraic tools are completely blind to smooth kinks, and the smooth analytic tools crash on simple topological spaces. Because our primary mathematical tools fail simultaneously on these objects, mathematicians are left flying completely blind when studying standard 4-dimensional spaces. To bypass this classification bottleneck, we have to stop trying to classify the entire 4-manifold and instead classify the surfaces embedded within them. For example, the unknotting conjecture asks if there is a unique, exotic 2-dimensional sphere embedded inside a 4-dimensional sphere. Because the gauge theory equations break down here, this problem remains completely intractable. The mathematical workaround is to cut the space open to create a boundary. Instead of closed spheres, we study a 2-dimensional disk embedded inside a 4-dimensional ball. This alters the math because the 4-ball possesses a 3-dimensional boundary, known as the 3-sphere. The edge of the embedded disk forms a knot situated on that boundary.
By fixing that boundary knot, topologists can have 2 distinct disks share the exact same edge and watch how they plunge downward into the interior volume of the 4-ball. To prove these disks are exotic, they must meet strict criteria. Their complements must have a fundamental group of Z, ensuring they are topologically equivalent, yet they must remain smoothly distinct. Slicing a mathematical space open creates a boundary that bypasses the breakdown of nonlinear partial differential equations. Topologists physically engineer these exotic spaces from the ground up using a process called handle-body decomposition. Because 4-dimensional volumes cannot be visualized, topologists build these spaces entirely by manipulating their 3-dimensional boundaries. The foundational component is a zero handle, which acts as a standard 4-ball. We represent this as a wireframe representing the 3-dimensional boundary of that 4-ball. The secondary component is a two-handle. You can think of a two-handle as a thickened two-dimensional disc. To build the space, this two-handle must be glued specifically along a framed knot located on the zero-handle's boundary. Handle body decomposition translates incomprehensible four-dimensional geometry into solvable three-dimensional knot theory. It allows mathematicians to literally build higher dimensions piece by piece. The difference between a standard manifold and an exotic one is not spread evenly across the space. It is entirely localized. The Cork theorem dictates that the entire difference in the smooth structure is confined to a single contractible submanifold inside the larger space. Topologists can physically isolate and extract this specific mathematical subsection, known as the cork, from the center of the manifold. Once extracted, they apply a mathematical alteration called an involution twist along the boundary of the cork. When the cork is glued back in place, it permanently warps the smooth calculus grid of the entire host manifold, despite leaving the macroscopic topological shape untouched. Exoticness is a highly specific physical kink. Topologists can locate it, surgically remove it, twist it, and reinstall it. Proving that exotic manifolds exist has moved from a research goal to a baseline assumption. Current work prioritizes quantifying the precise degree of smooth incompatibility between these pairs. To measure this, mathematicians use a metric called stabilization distance, or complexity. This chart shows complexity on the y-axis against geometric linking operations on the x-axis. It measures the minimum linking required to cork twist smooth structures. To achieve higher complexity values, the mathematical links inside the boundary model must grow increasingly tangled. There is a massive open question in the field. Are there pairs of closed manifolds that require a complexity distance greater than 1? We know that for manifolds with boundaries, recent breakthroughs have proven high complexity distances do exist. This expands the known map of four-dimensional space. Calculating stabilization distance turns the study of exotic manifolds into a rigorous problem of geometric knot complexity. The study of four-dimensional space is defined by the intense flexibility of continuous functions, clashing against the rigid rules of smooth calculus. Standard mathematical tools fail here. Algebraic topology is inherently blind to smooth kinks, while gauge theory equations dissolve on simple spaces. To study these structures, topologists must abandon standard analysis and rely wholly on the geometric engineering of handle bodies and cork twists. The ultimate, unconquered goal of this geometric engineering is proving or disproving the smooth four-dimensional Poincaré conjecture. Because four-dimensional space resists standard calculus, the geometric manipulation of handles and corks remains our most precise tool for mapping its structure.